What if the most terrifying message from the stars wasn't a broadcast, but an object? What if that object wasn't just visiting but reporting back to something else? In 2025, officials confirmed the detection of our solar system's third interstellar visitor, an object designated 3I Atlas. But as they decoded its transmissions and analyzed its impossible flight path, they confirmed a fear that humanity has held for centuries. This wasn't a random rock, it was a messenger. Let's explore this together. The impossible visitor. What if our third confirmed interstellar guest wasn't just wandering through space, but navigating it? When astronomical networks like Pan-STARRS first detected 3I Atlas in early 2025, it shattered every known classification. Unlike previous interstellar visitors, it was traveling at an unusually high interstellar velocity of 45 kilometers per second relative to our Sun, on a trajectory with a hyperbolic eccentricity of over 3.5. But it was its behavior that was truly impossible. It executed deliberate course corrections, moving with a precision that defied any natural explanation. This wasn't a random rock. Its massive coma, a gas and dust cloud stretching 700,000 kilometers across, pulsed with a steady, repeating electromagnetic signal, unlike the chaotic outgassing of a comet like Hale-Bopp. The trajectory it took was impossibly efficient, using the gravitational wells of planets it passed as if it had a complete map of our system, a feat that takes our own probes years of calculation to achieve. The sheer energy required for these maneuvers, conducted without any visible propellant, suggests a technology that operates outside our known physics. As 3I Atlas carved a path through our asteroid belt with surgical accuracy, it became clear this wasn't an exploration, it felt like an arrival. When physics stopped making sense. Here's where the story takes a sharp turn from a scientific curiosity into a genuine threat. Most objects from beyond our solar system follow chaotic trajectories, their paths dictated by gravity. But 3I Atlas demonstrated something entirely different. Its path allowed it to drift past several planets in ways that maximized gravitational efficiency, a maneuver that reminded JPL engineers of complex gravity assist routes they designed for probes like Voyager. When celestial mechanics experts like Jacques Lascar from the Paris Observatory ran the orbital simulations backward, they discovered something statistically impossible without intelligent intervention. The path of 3I Atlas required navigating through dense meteoroid streams and planetary collision zones with a mathematical elegance that was simply breathtaking. Its trajectory deviated from a purely gravitational path by a measured 0.05 arcseconds per hour. A tiny but constant thrust that had no visible source. It moved like a grandmaster's chess piece on a cosmic board, avoiding every conceivable threat with a precision that suggested either advanced, long-term planning or sophisticated real-time control. This wasn't a random space rock wandering through the cosmos, it was, as some scientists began to describe it, exhibiting piloted behavior. The object that defied reality. When NASA aimed the James Webb Space Telescope at 3I Atlas, the data it sent back challenged our understanding of reality itself. The thermal readings were the first red flag. Instead of chaotic heat bursts, 3I Atlas showed a consistent thermal signature of 250 Kelvin, pulsing with a precision of microseconds. JWST's principal investigator for the observation, Dr. Jane Rigby, noted that the thermal stability was unnatural. Webb spectrography then revealed hyper-reflective compounds that appeared artificial, a material with a near-perfect albedo of 0.98, reflecting 98% of all light, something not found in nature. But the most disturbing discovery was a faint electromagnetic pulse repeating every 147.13 seconds. It matched the signature of a real pulsar, PSRB 1919+21, yet the object had no magnetic field capable of generating it. It seemed to be mimicking a signal, a form of cosmic camouflage. Webb's infrared analysis also found structural patterns resembling recursive geometric fractals, leading some to float the terrifying consciousness engine theory, comparing it to theoretical concepts like a Matryoshka brain, but on a smaller, mobile scale. The combination of these impossible features in one object moves it from unusual to unequivocally artificial. Two visitors, one terrifying pattern. The mystery deepened significantly when researchers cross-referenced 3I Atlas's electromagnetic signature with archived data from Oumuamua, The comparison revealed something that, honestly, sent shockwaves through the scientific community. The exact same 147-second frequency had been detected briefly in Oumuamua's data, a faint 3 sigma detection that was at first dismissed as noise. But here's the thing. The crucial difference was that 3I Atlas's signal was a powerful, sustained 50 sigma detection, an unmistakable beacon. This discovery, championed by controversial Harvard astronomer Avi Loeb, completely reframed our understanding of both objects. Oumuamua had puzzled scientists, but now a disturbing pattern emerged. The evidence suggested that Oumuamua may have been a reconnaissance probe, and if this theory held merit, then 3I Atlas represented something far more significant. Not passive observation but active engagement. It was the difference between a single radar ping and a fully operational surveillance system. Some researchers now theorize that Oumuamua was the lock, and 3I Atlas is the key, designed not just to observe but to unlock something, whether buried on our planet or awaiting activation in orbit. When space objects make calculated decisions. The moment we knew for sure we were being actively monitored was the moment it changed course. Just as scientists believed they had mapped its future trajectory, the Very Large Telescope in Chile recorded a subtle but unmistakable 0.05-degree inclination shift, an adjustment of 180 arcseconds. This wasn't the random drift of a comet. The object veered off its projected arc, aligning with a new vector that brought it closer to Earth's orbital plane. To mission analysts like planetary scientist Dr. Sarah Seeger, the implication was clear. This was a conscious decision. The maneuver occurred just 72 hours after the James Webb Space Telescope began its focused spectroscopic analysis, a time frame confirmed by NASA's Deep Space Network that, honestly, rules out coincidence. This inclination shift is an incredibly energy-intensive move, and the action wasn't just responsive, it was almost defiant, a clear message that said, "We see you watching us." The mood at the DSN's Goldstone complex as they tracked this impossible change in real time shifted from academic curiosity to profound alarm. Ancient mathematics from the stars. As if its movements weren't enough, independent cryptographers at the SETI Institute, inspired by the lifelong work of pioneers like Dr. Jill Tarter, uncovered something extraordinary. Using Fourier analysis of the pulse's phase modulation, they found precise mathematical ratios hidden within the signal, the golden ratio, Fibonacci sequences, and the first 100 prime numbers encoded in binary. These weren't arbitrary concepts, they represent fundamental codes that appear throughout the natural universe. The precision of these patterns suggested a level of mathematical sophistication far beyond random cosmic noise. Even more disturbing was the dynamic nature of these signals. The mathematical patterns weren't constant, they changed subtly, reacting to solar activity and even our own radio emissions. Most chilling of all, researchers detected a brief disruption, a single skipped pulse that matched exactly with the moment James Webb first locked onto it. The object appeared to know it was being observed and had responded with a mathematical fingerprint that spoke a language older than human civilization itself. Organic chemistry from beyond the stars. It wasn't just a machine, it was carrying the very building blocks of life. James Webb's detailed spectroscopic analysis revealed its outer shell was coated in complex carbon molecules, and its NIRSpec instrument found evidence of adenine, one of the 4 nucleobases in DNA, via clear absorption lines between 260 and 280 nanometers. What was alarming was the purity and organization of these molecules. Unlike the chaotic racemic mixture of amino acids found in the Murchison meteorite, the compounds on 3I Atlas showed a 99.7% levorotatory excess, a homochiral signature that is a smoking gun for biological or artificial synthesis. Astrobiologist Dr. Heather Graham at NASA's Goddard Space Flight Center found the conclusion both thrilling and terrifying. The terrifying implication is that if this is a seed ship, its purpose might not be benevolent. It could be preparing the environment for a subsequent colonization effort. The presence of DNA components suggests a biology that might be eerily compatible or dangerously competitive with our own. When Earth responded to the cosmic visitor. The connection between 3I Atlas and Earth became far more unsettling when a classified high-altitude surveillance balloon managed by the U.S. Antarctic program detected something extraordinary. The balloon's instruments recorded a powerful microwave burst at 23.5 gigahertz, sharp and centered precisely above the South Pole. Initially dismissed as interference, its timing aligned perfectly with another angular shift in 3Y Atlas's trajectory. Moments after the burst, seismic stations that are part of the global seismographic network recorded ultra-low frequency rumbles across the frozen continent. These deep, resonant frequencies were a perfect 0.0068 Hz, the exact inverse of the 147-second pulses being emitted by 3Y Atlas. The synchronization was impossible to dismiss as a coincidence. Somehow, this visitor appeared to be influencing activity on our own planet, possibly triggering responses from systems buried deep beneath the Antarctic ice. The object wasn't just passing by, it was actively interacting with Earth in ways that suggested a technological sophistication far beyond our current understanding. The asteroid belt death run. Right now, 3I Atlas is navigating a cosmic minefield, and it's doing so with terrifying ease. Its current path takes it directly through the main asteroid belt, traversing the dense Kirkwood gaps at over 60 kilometers per second. Unlike most comets, which have highly inclined orbits, 3I Atlas is cutting directly through the belt's core. Planetary defense expert Dr. Amy Mainzer, former principal investigator of the NEOWISE survey, noted that its 700,000-kilometer coma is interacting with millions of untracked objects. More astonishingly, minor course corrections have been observed, suggesting it's actively avoiding even meter-sized debris with impossible precision. This avoidance system must be processing the trajectories of over 1.5 million known objects in real time, a feat of computation that dwarfs anything on Earth. Its journey isn't a dangerous run so much as a demonstration of effortless superiority over a hazardous environment, adjusting its path by mere hundreds of kilometers to avoid potential impacts. Rewiring our solar system's neural network. Scientists have now discovered that 3I Atlas's interaction extends far beyond simple gravitational effects. Its complex, dusty plasma envelope is actively interacting with the solar system's magnetic field, creating what researchers are calling an electromagnetic web effect. As 3I Atlas cuts through the inner solar system, it could be generating packets of charged dust that flow along the sun's natural electric currents toward Earth, potentially triggering geomagnetic storms. But the most disturbing discovery is the most recent. Observations from the Allen Telescope Array show that 3Y Atlas has begun emitting a secondary signal, a lower frequency, longer pulse at 700 MHz pointed directly toward the Orion constellation. As SETI astronomer Seth Shostak noted, a signal not pointed at us is infinitely more chilling. Some researchers believe it's calling for reinforcements. Others think it's reporting back on its findings. But either way, one conclusion seems undeniable. This was never just an interstellar rock. This was a node, a probe, a messenger, broadcasting to something else that is still on its way. The universe has sent us messengers, and we are only just beginning to learn their language. The mysteries of Oumuamua and other interstellar visitors remind us that we are part of a vast, interconnected cosmos filled with wonders we are yet to discover. The journey into the unknown continues. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the frontiers of science. Thank you for watching Simply Science. What if I told you the greatest journey in human history is about to get a sequel? For nearly 50 years, two probes, relics of the 1970s, have been our only eyes and ears in the vast dark ocean between the stars. But, their time is running out. Now, scientists are designing a successor, a true interstellar explorer built for the 21st century, powered by next-generation systems and guided by artificial intelligence. This is the story of humanity's next great leap into the cosmos. So let's explore this together. The original Voyager achievement. Ever wonder how two probes from the 1970s became the greatest explorers in human history? Well, the answer is a mix of brilliant engineering and perfect timing. Managed by the Jet Propulsion Laboratory, Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that happens only once every 175 years. This grand tour alignment allowed them to use gravity assists, slingshotting from one giant planet to the next. Under the guidance of scientists like the legendary project scientist Ed Stone, who served for 50 years, the discoveries were staggering. We saw active volcanoes spewing sulfur on Jupiter's moon Io, confirming 9 active eruptions and making it the most geologically active object in the solar system. We discovered the icy geysers of Neptune's moon Triton, a world so cold it spews nitrogen frost. These missions completely rewrote planetary science textbooks, all accomplished with custom-built computers that had just 69.63 kilobytes of memory, less than 1/1,000,000th of a single photo taken by a modern smartphone. They transformed our view of the outer planets from fuzzy telescope images into a detailed family portrait, revealing worlds more dynamic and complex than anyone had ever imagined. It was a mission of firsts, providing the data that forms the foundation of modern planetary science. A journey into interstellar space. So what happens after you complete a grand tour of the outer planets? You keep going, farther and faster into the unknown. After their primary missions ended in 1989, the Voyagers began the Voyager Interstellar mission. Their new objective was to reach the edge of the heliosphere, the vast magnetic bubble inflated by our sun's solar wind that shields the planets from about 75% of galactic radiation. For years they traveled toward this boundary. Then on August 25, 2012, Voyager 1 made history at a distance of 121 astronomical units, or 121 times the distance from Earth to the Sun. It crossed the heliopause, the final frontier of our solar system, and entered interstellar space. Stamatios Tom Crimigis, a lead investigator, confirmed the data was undeniable. Voyager 2, on a different trajectory, followed suit on November 5, 2018, at about 119 AU. Now, Voyager 1 is over 163 AU away, the most distant human-made object in existence. For the first time, we were getting direct measurements of the interstellar medium, data sent from a place no probe was ever truly built to explore. Current limitations of the Voyagers. Here's the fundamental problem. The Voyagers are technological marvels, but they are also relics. They were designed for the powerful environments of planets, not the subtle nuances of interstellar space. Their magnetometers, for example, were built to measure the powerful magnetic fields of gas giants, not the faint, tenuous fields between the stars. Their cosmic ray subsystem can detect energetic particles, but it lacks the sophistication to distinguish between different heavy elements with the precision a modern instrument could, which is critical for understanding the origin of these rays. Furthermore, their power source, which uses heat from decaying plutonium-238, is fading. The initial 470 watts of power has dwindled, losing about 4 watts of electrical power each year. To conserve what little energy remains, engineers on the ground are in a constant race against time, making difficult choices about which instruments to sacrifice next. Their data trickles home to the Deep Space Network at a mere 160 bits per second, meaning it would take over a week to send a single low-resolution photo. The signal is now so faint, billions of times weaker than a watch battery, that it requires the world's most sensitive radio antennas just to hear it. The case for Voyager 3. With the original Voyagers fading, the question isn't just about continuing their legacy, it's about launching a revolution in interstellar science. The scientific community, including visionaries like Ralph McNutt Jr. from the Johns Hopkins Applied Physics Laboratory, isn't talking about a simple sequel. They are proposing a dedicated interstellar probe. This concept, often nicknamed Voyager 3, would be a machine designed from the ground up for a 50-year mission to explore the interstellar medium. It would carry a suite of modern instruments specifically built to analyze the space between stars with a precision the Voyagers could only dream of. The goal is ambitious: to travel 1,000 astronomical units from the Sun, more than 6 times farther than Voyager 1 has traveled in nearly 5 decades. This isn't about nostalgia for the Voyager name, it's about a critical scientific imperative. The Voyagers proved we could touch the stars, but they left us with more questions than answers. A new probe would be our tool to finally understand our place in the cosmic neighborhood. Advanced technology capabilities. So what kind of upgrade would a modern interstellar probe get? Let me explain. Compared to the Voyager's 1970s technology, a new probe would be a revolutionary leap. Instead of limited sensors, it would carry a suite of advanced instruments: a plasma spectrometer, energetic particle detectors, magnetometers, and a dust counter, all with at least 100 times the resolution of the Voyager's equipment. Power would come from a next-generation RTG, designed for longevity and providing enough power to run a full suite of instruments for a century. But the real game changer would be its brain AI-powered autonomous systems. This would allow it to make its own decisions, acting like a true robotic field scientist. It could prioritize data, compressing less important information to save bandwidth for groundbreaking discoveries, and even react to unforeseen events without waiting for the 3-day round-trip communication with Earth. To achieve its speed, the mission would launch on the most powerful rocket available, like NASA's SLS Block 2, and perform a powered Jupiter gravity assist, using both Jupiter's gravity and an onboard engine to achieve velocities previously thought impossible for a long-duration science mission. The interstellar medium mystery. Why is it so critical to study the space between the stars? Because our solar system is not an island. It's a ship sailing through the interstellar medium, and the heliosphere is our hull. For years, we thought this protective bubble was shaped like a comet, with a long tail stretching behind it. But the data from the Voyagers, combined with models from astrophysicists like Merav Ofer of Boston University, suggests something far stranger. Her models indicate the heliosphere might be a deflated croissant or have two distinct jets, a shape no one predicted. The truth is, we don't know for sure because we only have 2 data points from the Voyagers. A dedicated interstellar probe with modern plasma and magnetic field sensors could finally map its true structure. It would directly measure the density of the local interstellar cloud our sun is passing through, about 0.1 atoms per cubic centimeter, and chart the strength of the interstellar magnetic field. Understanding this interaction is fundamental to knowing our place in the galaxy and the nature of astrospheres around other stars. Scientific objectives and research goals. Let's get specific. What questions would a mission like the interstellar probe finally answer? First, it would explore the unshocked interstellar medium, the pristine galactic material our sun is moving through. This means getting a baseline chemical inventory of our galactic neighborhood, the very stuff from which future stars and planets will form. Second, it would map the structure of our heliosphere in high definition, crossing key boundaries like the termination shock and heliosheath with far more advanced instruments. It would finally solve the mystery of its shape and reveal the physics of its interaction with the galaxy. Finally, the mission would journey to a target of 1,000 astronomical units from the Sun. As physicist Ralph McNutt from the APL team emphasizes, getting to this distance would allow us to look back and view our solar system as a complete astrosphere for the first time. From this vantage point, it could even detect the faint extragalactic background light without interference from dust in our solar system, opening a new window for cosmology and studying the universe's first light. It would be a multi-purpose observatory unlike any other. Practical applications for future missions. This isn't just about pure science, it's about laying the foundation for humanity's future in space. A modern interstellar probe would be a crucial pathfinder, charting the hazards of deep space. Its most important practical application would be creating the first detailed map of the radiation environment beyond our heliosphere. We know from Voyager data that the flux of high-energy galactic cosmic rays is roughly 3 times higher outside the heliosphere. These particles can damage electronics and pose a significant threat to biological life. A new probe would measure this radiation with unprecedented accuracy, providing the essential data engineers need to design shielding for future robotic and eventually, human interstellar missions. Understanding the plasma turbulence and magnetic field orientation is also critical for developing safe navigation strategies. Just as early sailors needed charts of ocean currents and reefs, future interstellar explorers will need a map of the interstellar medium. This mission would create that first map, making the next steps in exploration possible. Cultural significance and golden record 2.0. What message would you send to represent all of humanity on a journey that will outlast everyone alive today? In 1977, Carl Sagan's committee assembled the Golden Records. An interstellar probe would carry on this legacy, but a Golden Record 2.0 wouldn't be a physical disc. John Lomberg, the artist who designed the original record's cover, has proposed a digital successor. This new archive could hold petabytes of data, the entire human genome, vast libraries of art and science, and perhaps even messages from the public. The new message would have to reflect our more globalized, digitally connected, and perhaps more self-aware civilization. The very act of creating it forces us to reflect on our collective identity and what we would want to say about ourselves to the cosmos. How do you represent humanity's flaws alongside its triumphs? Who gets to decide? This probe and its message will travel through the galaxy for millions of years, long after Earth has changed beyond recognition. It serves a dual purpose: a scientific instrument pushing the frontier of knowledge, and a cultural artifact carrying the story of humanity to the stars, a true monument to our civilization. Timing and opportunity. Here's why this conversation is happening right now. The original Voyager's Grand Tour was a once-in-a-lifetime opportunity. To achieve the immense speeds needed for a true interstellar mission in a reasonable time frame, we need a similar advantage. As identified by Ralph McNutt and the APL team, a powerful launch window opens in the 2030s. A launch in 2036 using a powerful rocket and a Jupiter gravity assist would provide the optimal trajectory to reach the target speed of 20 astronomical units per year. Missing this window would mean waiting until the next alignment in the late 2040s, a significant delay for a mission that is already decades in the making. The technology needed for the core mission is largely ready or in advanced development. This isn't a far-off dream, it's an achievable plan with a clear timeline. The Voyagers have been our scouts, but their journey is nearing its end. If we want to build on their legacy rather than letting it fade into silence, the time to commit is now. The cosmos is waiting, and the launch window is opening. An interstellar probe wouldn't just be repeating the past, it would be a quantum leap forward. It would push deeper, answer fundamental questions about our place in the cosmos, and test the technologies needed for future missions to the stars. The first Voyagers were our first messengers to the galaxy, carrying a hopeful greeting from a small, distant world. This new probe could be our new voice, our new eyes, and our first true step beyond the sun's embrace. Are we ready to take that step? Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Simply Science. The biggest cosmic encounter since Oumuamua, and honestly the world's most powerful space agencies have gone completely dark. On October 3, 2025, an interstellar comet named 3I Atlas buzzed Mars, and, well, the only proof we have is a ghostly smudge found by citizen scientists in public data. With billions of dollars of technology pointed right at it, the official images are, missing in action. So, are we looking at a cover-up, a colossal failure, or maybe the quiet prelude to a discovery that will change everything? Let's explore this together. The flyby. You have to understand, this wasn't just another cosmic event, it was a rendezvous that scientists have dreamed about for decades. On October 3, 2025, the interstellar comet 3I Atlas made its closest approach, skimming just under 0.2 astronomical units. That's about 29 million kilometers from the planet Mars. To put that in perspective, that's closer than any planet ever gets to another, outside of a collision. This flyby was a moment of incredible cosmic alignment. For the first time, a visitor from another star system was set to pass directly through a region of space monitored by a dedicated fleet of advanced scientific instruments. Every major space agency with a presence at Mars, from NASA and the European Space Agency to China's CNSA and the UAE's HOPE mission, had a front-row seat. Mission planners, like Dr. Jim Bell, the principal investigator for Perseverance's Mastcam Z cameras, scrambled to redirect their assets. This wasn't in the original mission plan, but, an opportunity like this is too valuable to ignore. The calculations were precise, the stakes were enormous, and the entire planetary science community held its breath, waiting for a flood of data from our robotic eyes at Mars. The promise of Mars. This was never just about getting a cool picture. This alignment was a once-in-a-generation chance to answer some of the biggest questions in planetary science. Having a world-class laboratory already in orbit around Mars meant we could study 3I Atlas in ways impossible from Earth. Think about it. The Mars Reconnaissance Orbiter's high-rise camera could potentially see the comet's nucleus or any fragments breaking off. Spectrometers like Omega on Mars Express or the Nomad instrument on the Trace Gas Orbiter were ready to taste the comet's atmosphere. Dr. Nicholas Thomas, who leads the team for the CASIS camera, knows these instruments are sensitive enough to detect the unique chemical fingerprints of interstellar ice. Are the building blocks of life the same in other star systems? Is the water in this comet similar to ours? These instruments were designed to answer exactly those questions by analyzing the gases in the coma. It was a chance to perform a chemical autopsy on a pristine sample from another star system, testing every theory we have about how planets are made. Every asset was pushed to its absolute limit for this cosmic flyby. A faint signal emerges. With the world's space agencies silent, the first and only evidence of the flyby came not from an official press release, but from the hard drives of two persistent citizen scientists. Enter Björn Jansson and Kevin Gill, two names legendary in the community for their meticulous processing of raw space images. Working independently, they went directly to NASA's Planetary Data System, the public archive where raw data from missions like Perseverance is posted. Within hours of the data being downlinked, they began their digital excavation. Their process was painstaking. They took dozens of long-exposure images from the Mastcam Z camera, which were designed to look at the dark Martian sky. By aligning each image based on the background stars, and then digitally stacking them, they could amplify the faint signal of anything that moved through the frame. After methodically subtracting sensor noise and cosmic ray hits, a faint, diffuse patch of light emerged, right where 3I Atlas was predicted to be. It wasn't a spectacular photo, but it was monumental, the first and only direct confirmation that the interstellar visitor had made its historic pass. Their work stands as a testament to the power of open data. The auditable path. Seeing a faint smudge in an image is one thing, but, proving it's actually an interstellar comet and not just some random noise is another challenge entirely. The path to this detection had to be auditable, meaning every single step was documented and reproducible. The analysts started with raw, 29-second exposures from Perseverance's Mastcam Z camera. The principal investigator for this camera, Dr. Jim Bell, designed it for incredible scientific precision. For each image, the team had to find a matching dark frame, which is basically an image taken with the lens cap on, to map out and subtract the camera sensor's inherent electronic noise. Then came flat field corrections to account for dust on the lens and variations in pixel sensitivity. Next, they had to align or register each image with sub-pixel accuracy against a star catalog. Only then could they stack the dozens of clean frames. They used multiple methods to combine the images, which boosts the signal of a faint object while averaging out random noise. The final step was to model and subtract the Martian sky's background glow. And, well, what was left was the detection. A signal statistically strong enough to be real. This wasn't just guesswork, it was a forensic process. Viral myths and reality checks. In the vacuum of official information, the internet did what it does best. It generated myths. The moment that faint real detection began to circulate, so did much more dramatic but fake images. The most viral was a sharp, razor-thin streak of light in a single frame from Perseverance's navigation camera. It was hailed as a naked-eye view of the interstellar comet, but the truth required a dose of orbital mechanics. Dr. Emily Lakdawala, a renowned planetary scientist and author, did what any good scientist does. She checked the numbers. Using JPL's Horizons Ephemeris tool, which can predict the position of any known object in the solar system, she plotted the streak's path and timing. The verdict was undeniable. The streak perfectly matched the speed, orientation, and sky path of Phobos, Mars's inner moon, during a long exposure. The second myth was a bright, fast-moving streak in a different Mastcam Z frame. Again, the math just didn't add up. Its angular velocity was at least 10 times faster than 3I Atlas was predicted to be moving. It was likely a meteor in Mars's upper atmosphere, or a simple sensor artifact. These episodes were honestly a critical lesson in scientific literacy. Not every streak in the sky is a visitor from another star. The silent orbiters. So, where were the multi-billion-dollar orbital missions while citizen scientists were making the only public detection? The silence is what makes this story so strange. Let's be clear about what we're missing. The Mars Reconnaissance Orbiter carries the HiRISE camera, a telescopic instrument so powerful it can spot a coffee table on the Martian surface from 300 kilometers up. Its principal investigator, Dr. Alfred McEwen, and his team could have delivered the sharpest image of an interstellar object ever seen. The ESA's orbiters were ready to perform a chemical analysis. The trace gas orbiter can detect atmospheric gases in trace amounts. If 3I Atlas was venting anything unusual, any molecule not seen in our own comets, it would have found it. The UAE's Hope and China's Tianwen-1 were also observing, providing a global network of coverage. The potential for a breakthrough was immense, yet as of today, not a single raw image, spectrum, or even a low-resolution thumbnail has been released to the public. The data is either under embargo, stuck in a processing queue, or, well, maybe something else is going on. The knife's edge. You know, the silence from the space agencies probably isn't a conspiracy. It's really just a reflection of the brutal reality of deep space operations. I mean, pointing a spacecraft at a tiny, fast-moving object millions of kilometers away is honestly an exercise in controlled terror. The ephemeris for 3I Atlas, its predicted position, was being updated, like, hourly. But here's the thing, the orbiters can't just react in real time. The commands to turn, point, and shoot have to be programmed and sent hours or even days in advance. It's what engineers call open-loop pointing. You shoot and pray the target crosses your field of view when you scheduled it to. Then there's the Deep Space Network, that communication lifeline to Earth. Every single bit of data, from every mission at Mars, has to compete for limited bandwidth. A historic image from high-rise might have to wait in a queue on the orbiter's solid-state drive for days, stuck behind higher priority engineering telemetry, and, you know, a single missed DSN window, or even a slight drift in the comet's predicted path could mean the difference between a Nobel Prize-winning image and a frame filled with empty black space. This, right here, is the knife's edge of interplanetary observation. Blinded by the sun. Just as the mystery of the missing data deepened, the curtain came down on any new observations from Earth. And, you know, this isn't a conspiracy, it is just orbital mechanics. As October advances, 3I Atlas is approaching what is called superior conjunction, when it passes almost directly behind the Sun from our perspective. This celestial alignment, happening around October 21st and 22nd, effectively blinds us. The Sun's overwhelming glare makes it impossible for any ground-based or near-Earth telescope to safely observe the comet. The comet's most active phase, its closest approach to the Sun, or perihelion, happens on October 29th, right in the middle of this blackout. As Dr. Michael S. P. Kelly has noted in his research, this is the most critical time to observe a comet for outbursts. It's when the comet should be at its most dynamic, and we are completely unable to watch. This blackout will last until early December, so for now, the silence from the Mars orbiters is compounded by a physical barrier. The universe itself has blocked our view, leaving us to wonder what is happening in the glare. The working hypothesis. Based on the limited data gathered before 3I Atlas disappeared into the Sun's glare, scientists have a working hypothesis, but, honestly, it's full of questions. The current theory is that 3I Atlas is a natural interstellar comet, but one with a very strange chemistry. Early spectra suggested it is rich in carbon dioxide ice, but surprisingly poor in dicarbon, the molecule that gives most of our solar system's comets their classic green coma. This points to an origin in a star system with a very different chemical makeup or temperature gradient than our own. Some of the provisional reports also hinted at a possible excess of metals like nickel in its dust, a finding that, if confirmed, would be truly bizarre and hard to explain. Dr. Stephanie Milam, an expert in comet chemistry at NASA, would be chomping at the bit for the orbiter data, as only high-resolution spectra can confirm these tantalizing hints. Without that data, the natural comet scenario remains just that, a hypothesis. The real proof is still sitting on a hard drive, waiting to be processed. What remains and what comes next? The data from the Mars flyby might be out of reach for now, but the story is not over. There are a few long-shot possibilities for observation during the solar conjunction blackout. The SOHO spacecraft, which constantly stares at the Sun, has a coronagraph called LASCO C3 that might catch a glimpse of the comet. It's not very sensitive, so it would only see 3I Atlas if the comet had a major outburst and brightened dramatically. Farther out in the solar system, the European Space Agency's JUICE spacecraft is on its way to Jupiter. Experts like Dr. Geraint Jones have confirmed that there might be a brief window in early November where JUICE could try to image the comet, but the real action will begin in late November or early December. That's when Earth's motion carries us out of the solar glare, and ground-based telescopes can finally get back in the game. When that happens, expect every major observatory to be pointed at that patch of sky, trying to recover the faint, receding visitor. Until then, the only confirmed public detection remains that single, faint stack of images from Perseverance. The story of 3I Atlas is a cliffhanger. We have a confirmed detection, a mountain of unanswered questions, and the most important data in a generation locked away, waiting for processing. This event has exposed both the incredible power of our robotic explorers and the frustrating limitations of deep space science. Was this just a strange comet, or is it something more? The answer is coming, but for now, we wait. This is a powerful reminder that the universe still holds deep mysteries, right on our cosmic doorstep. Don't forget to like, subscribe, and hit the bell icon for more explorations into the cosmos. Thanks for watching Simply Science.